Hi guys. So some of you actually found out that I actually gave a talk like 3 years ago at DEFCON 4, so the conference of the official Ethereum conference, basically. And it was actually this talk recorded in video. And the main idea with this talk was to discuss about reversing Ethereum smart contract, EVM bytecode, and what are basically the difficulties and the main issue when you are dealing with EVM bytecode reversing. So if you want to take a look at the video, I will put the link directly below. But basically, I took the slide back, and I'm planning to for today to discuss about reversing EVM smart contract and give you a bit more detail about like the main issue and so on, and do like a quick version of the talk, and also to show you directly in live what you can see directly in Etherscan and so on. So a bit of a demo as well. So yeah, the main idea is to reverse EVM bytecode, and for that there is multiple points that are really interesting. Especially you need to disassemble the bytecode, and after that you have all kind of stuff like CFG reconstruction, function identification, function name recovery, and so on. So it's gonna be really interesting if you are doing, like, for example, basically security audit on closed source bytecode, but also even for if you have the source code, it's still valuable, especially if you want to understand like optimization and how exactly it works, and how like a given transaction is coming to the smart contract and how it is interpreted internally. So it's basically a really like in-depth overview of how a smart contract work inside. So let's start with a quick intro. So basically, reverse engineering is the idea that you have the closed source, you have only like the bytecode, and your goal is to recover and to understand, to reverse the logic and understand just from the bytecode what is happening. So basically, you have some Solidity source code. It will be converted into EVM bytecode, and reversing is the fact of going from there, this bytecode, into something more appealing. So in that case, it's just disassembly, because we are just interpreting the different byte, but we have a bit more than just that, of course. So in that case, we have the EVM assembly right there. So if you take a look at the bytecode, you can decompose the bytecode. So if you are taking this input from the first transaction, when you are creating the smart contract, you will basically see you can split that in multiple parts. The first part is basically the loader code. So it's the bytecode that will create the smart contract. So it's basically the constructor of the smart contract. And then you have the actual runtime code. So all these bytecode are basically the smart contract that will be stored on the blockchain, and that will be interpreted and executed each time you are doing a transaction against him. Then you have the swarm hash. I mean, it's not mandatory. From time to time you can have that, and basically you will get like a hash, an address to like, I don't know, like IPFS or something like that, and basically you can put, usually we are putting basically the source code of the contract, but yeah, it depends. So this smart contract will be executed by the Ethereum virtual machine, so the EVM machine. I think there is a bit more instruction set right now, but it's basically a stack machine, Turing complete. You have multiple opcodes that are available, and you have especially multiple type of memory. So that's something really important. You have the stack, the memory, and the storage. What you need to remember in that case is that only the storage is persistent. So basically, if you want to store something on your smart contract, that will be stored forever, basically, or that can be like modified later and so on, but that will be basically something persistent. You will need to use the storage for that. You can think of I don't know, for example, who is the owner of the smart contract. So this information will be stored persistently. So that's the idea. Then you have we are doing a bytecode disassembly. So the main idea is, as I mentioned, to take the bytecode right there and to convert that into something more readable for us. So in that case, into EVM assembly. As we can see, we have multiple push, store, and stuff like that. So we can already start to understand what the contract is doing just by taking a look at the bytecodes. So in order to do that, we need to be aware of the instruction set, and especially we need to associate each opcode value to the correct instruction. So in that case, we need to have the an instruction set table, basically. And as you can see, depending of the family of operation, we will be in one range or another. But you can basically find all of that directly on internet. It's complicated. I mean, it's part of the EVM documentation. So, for example, we have like the block hash, Coinbase, dupe, swap, stop, add, and so on. So a bunch of them. And that's what allow us to go from there, like 60. And it will allow us to understand, okay, 60 is actually a push one something. So actually 60 is push one and 80 is the OX80. It's the value and so on and so on. So that's nice, but if you are familiar with reverse engineering, usually that's not enough for us because the main issue is everything is linear. In that case, we are reading everything in this order, and it will be complicated for us to basically, when we will reach like a jump, some particular instruction, those instructions will allow us to jump into somewhere else in the code. So it's gonna start to be painful for us to basically follow the pattern and follow the execution flow of this smart contract. That's why we need to reconstruct the CFG, the control flow graph. So basically, the control flow graph is a graphical representation of the logic of the program. And we are using for that basic blocks and edges. So basic blocks in that case are basically the circle, and edges are basically the arrow right there. So as you can see, if we want to graphically represent like a if then else, it will look like that. We are entering into the if, and depending of the value, if a equal 1, in that case we will go there, in the other case we will go there, and then we are going to the same point and so on. So graphically, pretty quickly, we're able to determine, okay, if it's a if then else condition, it's a while, it's a switch, it's a for, and so on and so on. So just graphically, we can do that. So in order to reconstruct this kind of stuff, we need to be aware of the control flow instruction. So that's basically the instructions that will determine the end of a basic block and that will allow us to basically cut the EVM bytecode into basic block, and then we will need to create the edges between all of them. So for those opcode, we have like jump I. We have everything that will halt the execution of the smart contract, like return, stop, invalid, self-destruct, and so on. And we also have like jump dest and some other stuff. So all those ones, basically, when we are reaching those opcode, especially so those ones, that means it's the last instruction of the current basic block. And for this jump dest is basically the first instruction of another basic block. But you get the idea. So from this linear EVM set of EVM instruction, we are able to basically create multiple basic blocks that will basically fit what we just mentioned, like self-destruct is the last one. In this case, we have jump dest, jump E, some linear piece of code, jump dest, and so on. Okay, so we are converting this linear stuff into basic block. So it's already a huge step because we know that when we are entering inside this basic block, there is nothing more that will escape. If we are entering inside this one, we will execute all the instruction. That's for sure. So let's continue. Right now, the main goal will be to basically identify the edges. So we need to understand that this basic block will be associated to this one or this one and so on. So there is multiple way to identify which edges is associated to which one. The first one is to do like a static analysis. We are just taking a look at the code as it, and we are trying to understand. Basically, for this example, we have, for example, push to 68, jump high. That means if we are doing the jump correctly, it's a conditional jump, we're going to go to the 68 position. And in that case, 68 is this one, jump test, it's correct. So we're going to go to this one. And if we are not doing the jump, we're going to just continue the execution. So after 4B, it will be 4C. And in that case, we're going to go to this one. So as you can see, just by statically taking a look at the code and understanding the different opcodes and the values, I'm able to understand that this that's the current flow. And after this basic block, I will go either to this one or either to this other one. Okay, purely statically. The main issue with that is this stuff will fail, especially when you will get the position that will be put on the stack. That means you will get some stack operation that will manipulate some data, and after that you will basically pop the value from the stack, and you will use that in order to define where you're gonna jump. So that's an issue. For example, in that case, we have some pop, swap, and jump. That's one basic block, but as you can see, if we are not aware of the stack, the different stack values, we are not able to understand where this jump will go. So that's really problematic stuff. And that means it's not possible for us to do that with static analysis. We will need to do dynamic analysis, or at least interpretation and or emulation of the stack value. To give you an idea, that's a graph that we can create just by doing static analysis. But as you can see, we have multiple basic blocks that will basically be orphaned because we are not able to understand where they are in the graph. Also, as you can see, the graph is a bit messy. And that's after doing dynamic analysis and especially stack evaluation. As you can see, we still have one block that is there, but it's not really important for this one. And after that, we have something that is pretty clean. As you can see, we have an entering block. This one, we are going either there or there, and so on and so on. So we have something that is more clean visually, and you're gonna understand why right now. So once we have a good graph like this one, something really nice for us will be to identify which functions are associated to this one. So basically, the graph you saw previously is the classical pattern for a switch. So as you can see, we are entering in the block 0, and depending of the different test we're going to do on all those blocks, we're going to go in one branch or another. In order to do that, we will need to understand those different functions, and we will need to identify those functions. Okay, so the runtime code entry point is the dispatcher function. So it's this one, what we call the dispatcher function, this big function right there. And basically, you are entering into the smart contract. And what will happen is that there is some comparison against 4 specific bytes that will be on the transaction payload. It's actually the first 4 bytes. And depending of the first 4 bytes of the transaction payload, we will go in one branch or another. So we can see that right there. We have the entry point right there. We are going there. push 4, we have this value equal push to 51. Okay, so what is happening is previously in the code, we are extracting the first 4 bytes. We are pushing this value, 41, C0, and so on. We are doing a comparison with the equal keyword, so it will pop the 2 values from the stack and compare the result. And depending of the result, we are going to the 51 or not. So we are going in that way or not. Otherwise, we are going in this side. This side, you can see dupe 1, push 4. So we are pushing another 4-byte value, and we are comparing if it's equal or not, and we are pushing 2, jump I. So we are going in this way if it's equal or not. Otherwise, we are going to another one. So, okay. So this tiny piece of code basically is testing like 2 signatures, and if the 2 signatures are not matching, we're gonna do like a revert. So we are interrupting the execution flow of the program. So those 4 bytes are the function hash, and that is the function offset. So that's the beginning of the function that we want, and in that case, this one. So let's, so that's the global dispatcher function, as I mentioned. And basically, after identifying all the functions, we are able to determine something like that. So for this smart contract, we can see that we have the dispatcher function right there. And then we have 7 callable functions, 1, 2, 3, 4, 5, 6, 7, and the default cases that is there, that usually is like a revert, because that means you are not you are not providing a valid function hash. So interesting, but it's not enough. We can actually even recover the name of the function just from the closed source bytecode. So for that, we are actually leveraging on the way those 4-byte function hashes are generated. Basically, it's using this specific formula. We are taking basically the prototype name with the different arguments and so on. We are encoding all the stuff, and we are getting some 4-byte stuff. So for example, if the function name is kill, it will be this hashes, and if it's greet, it will be this one, and so on. Okay, so nothing really fancy there. But the good part for us is that we can actually brute force, and we can actually, if it's the same function name and same argument, it will be the same hashes. So that's pretty good for us. These function hashes are used, as I mentioned, on the transaction. For example, if I'm calling this method, you can see that the method ID will be this one, and actually this one, 41, will be the kill method. So by taking a look at, we know that it's a function kill because the method ID is this one. So let's continue. If we want basically to reverse the stuff, we can do it as well, because in that case, we can use something like that, the Ethereum signature database. And let me, for example, just take a look at this one, for example. If I'm providing this signature and I'm searching, I will get as a result. Okay, strange, getting nothing as a result. Okay, so we need to remove the OX. But as you can see, this signature corresponds to kill. Okay, so that's what we was thinking about. So that's nice. We are able to recover the signature. Just we are able to recover the name of the function and the argument type just by doing like a reverse loopback on the signature on the function signature. So in that case, we have greet and kill, and that's the smart contract that I was showing you previously. And something also interesting is that basically, since it's using also the arguments types, that means for two functions that are almost using the same stuff but not the same type, we will not get the same signature. So it's really, really accurate, and you can recover both the function name and the argument. Same time. So before discussing why we need to do reversing more in deep, the first reason, of course, is already that right now you are able to understand a bit more how it works internally and why with one transaction you are able to call multiple functions. That's because of the dispatcher function. But let me show you a bit more of that with like on Etherscan. This contract is the Bored Ape contract. As you can see, we have multiple transactions. That's okay. We have the contract right there. If I'm taking, let me zoom in more. We have the contract right there. So we have the source code that is provided. So in that case, it's because they decide to provide the source code to Etherscan, or they basically provide that into IPFS. So it's directly linked by Etherscan. So we have the contract. Let's say we don't have it. We have the contract ABI and we have the contract creation code. So that's the bytecode I was mentioning. Then we also have the constructor argument. So that's interesting, especially to understand who was the creator of the smart contract and which argument was used to create this stuff. Basically, as you can see, we have arg 0, 1, 2, 3. So you will basically maybe get some specific supply value, some addresses, and so on. And then we have some other stuff. We have the swarm source and so on. So this bytecode is actually what I was telling you. What can you do with that? Is it possible for you to understand what is happening without taking a look at the smart contract? So what I was mentioning is basically taking this stuff and, for example, the decompilation could be done really easily using the switch to opcode view. So you are clicking right there. You will basically generate the opcode view. So that's what I was mentioning with push one, M star, and so on. But everything is linear, so it's not really easy to understand. And that's why we need to do some other stuff. And in that case, you can even see that it's failing because there is some unknown opcode right there. So something wrong is happening on the disassembly of the bytecode. You can also do decompilation. I'm going to mention right after what is it. But basically, the main goal would be to, based on those bytecode, convert that into Solidity source code. So it's definitely another story. It's a more advanced technique when you are doing reversing, but it's not something we're going to discuss right now. So just to finish on that, why you want to reverse a smart contract, there is multiple reasons. First of all, if you want to do like due diligence, understand the logic, or even do some CTF challenges, because what you need to remember is that basically providing the source code of a smart contract is not mandatory. So you can, the only stuff that is mandatory is basically the bytecode of the smart contract, that's all. Also, it could be interesting to do reverse engineering of closed source smart contract. You can think of the famous CryptoKitties Gen Science contract. That is the contract in charge of creating the gens for kitties. Basically, this smart contract is not public. We don't have the source code of the smart contract, or at least at the time it was not available. I don't know if it's still the case. But basically, it was not possible for people to understand all the generation was done. And that's why it was a closed source. So basically, what people decide is actually to reverse the smart contract to understand the logic. And by doing that, I was able to recreate the algorithm that was used. And there was basically able to reverse and create kind of a generator, an analyzer of the gen mechanism, meaning that you can directly go to those website and take a look at those blog posts, and you will basically see how they have been able to reverse the stuff, and how you can basically anticipate what will be the result and what your CryptoKitties can look like in some particular cases. So that was really interesting. It's also really interesting for company in general, like the app company and so on, for security audit, but also for everything regarding bytecode optimization or understanding how it works. A good example was Ryan some years ago that was actually taking a look at the generation of the Solidity compiler. And he found out that actually the Solidity compiler at the time was doing exponentiation on a constant. And so it's definitely not optimized because you can just replace that with constant and calculate the stuff, and it will prevent using the exponentiation opcode. And in that case, you're going to save some gas. So in that case, for example, exponentiation of two constant, if you are there, if it's two constant, you can just calculate directly the result at compilation and put that as a push result instead of an exponentiation. That will be way better, and so on. So after this discovery, there is Martin from the Ethereum Foundation that actually have tried to reproduce and analyze that in the real life and see for other usage of exponentiation. And the final result was very interesting. On 16 random blocks, there was like 73% of exponentiation in invocations that could be optimized. So that means a lot of gas was basically burned for nothing because if your Solidity compiler was optimized, your EVM bytecode was optimized, you will be able to save some gas for your user and even for you when you are basically pushing everything. So really interesting, a really good application, not just for security, but also for development in general. You can also use reversing for security research, bug hunting, vulnerability research, and so on. Basically, a bunch of tools exist. You can think of Mitril, Echina, and so on. Basically, all those tools are not using usually like the Solidity source code, but they are actually using the EVM bytecode. And you can perfectly use all those tools just with the EVM bytecode directly. So that's also why it's interesting. And finally, also for like I put threat intelligence team at the time, but it's everything regarding like monitoring and analyzing transaction that you have and smart contract interaction. That's something really interesting, especially when you have some smart contracts that have been destroyed by the time. So everything regarding like post-mortem analysis. In that case, you will need to reverse the smart contract because, as you know, when basically a smart contract is destroyed, you don't have access to the bytecode anymore. But the fact is, since the smart contract have been created with a specific transaction, the creation transaction, you can recover the smart contract bytecode. Using that, you will get the loader code and the runtime code. So you will get both, and just based on that, you are able to reconstruct the smart contract. So that's really interesting, really useful if you are analyzing like past transaction or if for some reason, a contract has been destroyed or whatever. That's something really interesting. That's the only way. Reversing is the only way to recover that case. So that's all. So I hope you learned a bit more about all the basically the EVM smart contract are working internally. Why you only have like one transaction, you are able to call multiple functions, how it works, and how everything interact with each other. If you want to do reversing of this stuff, there is multiple tools available. I will let you find them. There is a bunch of them. For example, you have the GBD compiler, you have the Ethersplay binary ninja, you have the EVM dis, and so on. So you have a bunch of them available. Let me know in the comment if you want a dedicated video about like reversing, like live reversing of EVM smart contract. And also I mentioned quickly about decompilation. So for example, this one was the Bored Ape contract, and you can decompile it. And as you can see, it's using the panoramic decompiler in that case. But as you can see, the decompiler actually failed on some function. And the main goal is from this stuff is able to reconstruct a Solidity smart contract. So in that case, something like that. So it's interesting. It's definitely not the same smart contract. It's just helping you to create something that will maybe be more readable for you. In the same way, you can also use, for example, this one, the EVM decompile stuff. You have some existing stuff, and if you are copy pasting the stuff, maybe we will get something. No. So as you can see, this one, so for the Bored Ape smart contract actually failed. That's it told us it's maybe, yeah, it's maybe the, oh, okay, interesting. Yeah, maybe he's not happy because it looked like constructor bytecode, so you will need to remove the constructor bytecode, the loader code from this part before doing the decompilation. So I mean, I will let you give it a try and see if you are getting some good result. But that's basically the idea. We can try to reconstruct the stuff. Let's see if just with the address it will be a bit more happy, maybe. So let me know on the comment what you would like to see. Oh, interesting. So as you can see, with this address is it succeeds to identify multiple public methods. So you have everything right there. There is some unknown method right there, some internal methods. Okay, interesting. And you have a decompilation result. So that's also really nice. So in that case, you don't need to deal with EVM bytecode directly, but you have like a better representation of the stuff. But it's a huge smart contract, definitely. Okay, and and pretty good. You even have the disassembly with like the snippet of code and some documentation and some comments that are really interesting. Okay, so let me know what you would like to see in the next blockchain security video, basically, and hope to get a lot of feedback from you. And please let me know also in which cases you are using EVM reversing and EVM disassembly code. Thank you. See you next time.